Yeah. Now, because the next slide isn't queued up, I have to. Oh, actually, you have the next one. You do? Okay. So once again, I get the deep privilege of introducing Nathaniel Frissell. We say nice things to Nathaniel Frissell. We complain loudly that he's not opening these talks with baby pictures. Papa, what are you doing? It's first kid. I mean, you're supposed to have pictures. You know, the fourth kid you don't take any pictures of, believe me, but the first one, yeah. So anyway, Personal Space Weather Station.
Yeah.
Nathaniel.
All right, thank you, David. And I think this will be the last formal talk for me for this conference. Got
Oh, stop that.
All right, so in the program, this says overview for a personal space weather station, but I changed the title a little bit. It's now science questions for a personal space weather station. And as some of you know who have been following the listserv, a lot of questions has come up. What are we actually doing with this personal space weather station? So I'm going to give a brief overview of the space weather station, and then some people in this room, Ethan Miller, Bill Erickson, Hyomin Kim, myself, we've been chatting about what types of science questions we could answer and address. So I'll give a few possibilities at the end. But to start off with, a personal space weather station. So this is just a reminder slide to show the big picture of the coupled geospace system and the ionosphere. We looked in my last talk at how solar flares and geomagnetic storms can really influence the ionosphere. And here we have the sun, you get your flares, you have the solar wind. Some of that energy goes directly down into the ionosphere through ultraviolet. As you have ultraviolet energy, just goes right down, hits the upper atmosphere, causes ionization. But you also have particles and magnetic fields that will stream along field lines and interact with the magnetosphere and end up down in the auroral zone, and you get all sorts of interesting magnetospheric physics that isn't quite as direct as a simple solar flare. And we also saw that in the last talk when we looked at the response to the geomagnetic storm. It was much more complicated than the solar flare response. And down here, this is the world that we as ham radio operators tend to live in, working with the ionosphere. And this is basically, you can also think of the ionosphere as a way of remote sensing the entire geospace system, the magnetosphere, etc. So, space weather station goals. As hams building a personal space weather station, what do we want to do? I think hams in general tend to think more in terms of operations. What are the best frequencies for working DX? How do we understand the RFI environment? Can we communicate better during emergencies? So those are very operational questions. But as we're running this ham-sci collective here, we're starting to learn that there's also many hams who are actually interested in the scientific research side of things. And so scientists often ask, can we better sample the environment? Can we better understand the near Earth space? And why do we want to do this? We really want to advance scientific understanding, not just, we don't want to just sample the environment to sample the environment or engineer things to engineer things, but we actually want to advance scientific understanding of the natural world around us. And so from a ham side, the science part of things, that's really the ultimate goal of the science. So we've shown this slide before. This is a terrestrial weather station that you can go buy off of Amazon or at Walmart or somewhere else. And people all around the globe will set these up in their backyard, and they can measure things like temperature and wind speed and rainfall, and all this information gets sent back to a central database like Weather Underground, and then people can either use it for operational things like we just talked about, or people can go back and mine that information. And so the question of the personal space weather station, which I really have to give Ward Silver credit for this original idea of saying this is what we should do next. We should set up a number of instruments like this that we can put together in an inexpensive package and do the same sort of thing for space weather. And this is my diagram that I drew up thinking about these ideas. Very simple. We have what instruments might go into this. We have our antenna and I often think of this as an HF antenna. I'm a very HF ionospheric thinking type of person, and you might have a rather general software-defined radio, kind of like, we've seen the Kiwi SDRs, the red Patayas. We're going to see many more of these things over the next day or so. And a software-defined radio instrument that's general enough that if you just run the correct app or the correct processing scheme on IQ data that comes out of it, you can get all sorts of different virtual instruments. And that might be disciplined by a GPS-disciplined oscillator or other very good oscillator. You might have a magnetometer, and Hyo-Min Kim will be talking more about magnetometers a little bit. And all of that information will go into a single board computer, be reduced a bit, sent off to the internet, and then off to a public database. So we've talked about all of this before. And target specifications, again, useful to both ham radio and space scientists and the space weather communities. Should be fairly inexpensive, modular instrument design, small footprint, nice user interface, local display, standard format we've talked about for sending data back to a central repository, open, community-driven design. So this is where it gets a little bit different. One of the things I was thinking is, what can we really sense from the ground? And going back to that diagram I just showed you, I basically had two things, a software-defined radio and a ground magnetic field. And people ask, well, what are you measuring? Well, if you listen to radio signals through the ionosphere, our main goal is basically to measure electron density as a function of altitude and latitude and longitude, basically know the electron density everywhere at all times, and then you can back out a lot of the physics from there. Conversely, we also want to know the ground magnetic field. If you have a ground magnetometer, Hyo-Min will talk about how you can sense currents in the ionosphere and the magnetosphere from the ground. And then if you put the information from all of these instruments together, you basically make one super instrument. As Phil likes to talk about, the instrument's really when you put all of the data from all these different sensors into a computer and you look at it together, then you actually have like a new instrument that's a virtual instrument from all of the data. But it's really, these are two things we can easily sense from the ground. Radio signals that have been modulated by the ionosphere, by listening to signals of opportunity, which we've heard about today, and also ground magnetometer data. Okay, so here's where it really gets different. And this is where we're trying to figure out what are the questions that we're going to be asking. Now, I should tell you, tomorrow afternoon, after the demo room at 4:15, we're going to have a panel discussion where these slides right here are basically serving as our jumping off point for the panel. We want to talk about the science questions. Also in these slides, this is the start of something that they call a science traceability matrix, where it defines what our investigation objectives are, what our science questions are, what our functional requirements are, and then eventually you'd extend this matrix to include, the instrument specifications and things like this. So this is just the first few parts. So what I'm going to do right now is I'm just going to show 3 objectives and show some science questions, and then these are going to be things that I encourage you to think about over today and tomorrow, and to talk amongst yourselves during the breaks and at the dinners and stuff. And when we hear about these instrument engineering talks, think about how the instrument engineering that we're talking about this afternoon, how that fits or could be changed to better address or help some of these science questions. Or conversely, do you have a science question that we're not answering? So let's start with objective number 1, and that is to characterize the ionospheric and geomagnetic response to space weather sources, space weather events with sources both from above, meaning space, and from below the ionosphere. And the reason I say that is most of us right now, we think about what causes ionospheric disturbances or ionospheric events, propagation events. We usually think in terms of sunspot numbers, X-ray, solar flares, geomagnetic disturbances. These are all things that come from space. So that's what we mean by things from above. From below, we heard some of this earlier when Bill talked about Joe Dziekowicz's idea of these upper-level lows causing sporadic E. Or in my research, I've looked at traveling ionospheric disturbances that were tied with atmospheric gravity waves that were associated with the polar vortex. So these are things where the neutral atmosphere, things from below, are coming up and affecting the atmosphere. So for the science questions, what are the characteristic temporal and spatial scales of magnetic fluctuations in near-Earth space during geomagnetic disturbances? And so this could come from Yeoman's ground magnetometer. How does ionospheric density vary as a function of location, altitude, and time in response to space weather disturbances associated with driving events such as solar flares, geomagnetic storms, substorms, and lower atmospheric perturbations? And you can see some of the presentations we've had today have already started to answer some of these questions. So functional requirements to address the magnetic fluctuations. We want to determine the ground magnetic field, the vector magnetic field, so we want to know it in the north-south direction, the east-west direction, the up-down direction, and that way we can start to localize what direction the currents sensing are going. And we want to be able to identify large geomagnetic disturbances, like the sorts of things that might cause power outages if you have ground-induced currents, and even very small events like something called micropulsations or ultra-low frequency variations in the magnetic field that can really tell you something about the geospace, the magnetosphere, way out into, say, the tail region, or right along the magnetopause. For the ionospheric one, we want to be able to receive transmissions from controlled sources that either we set up or signals of opportunity. We've talked a lot about WWV today. Ethan Miller can tell you a lot about something called CODAR, which is a ocean HF radar that he is able to use and basically get oblique ionospheric soundings just by listening to these things. So objective 2 would be to characterize ionospheric variability and identify its sources both during quiet and disturbed times. I want to call attention to this word variability here because, when we talk about space weather, we don't really understand space weather that well. We have a good understanding of space climate. We understand these long-term variations of, say, the 11-year solar cycle. We understand basically diurnal variations, day-night differences, but things that happen on minute-to-minute or hour-to-hour timescales, or these things that just suddenly pop up, we don't understand those so well. So we want to be able to characterize them, just measure them, and then try to identify what's actually causing these things. So for the science questions here, we might ask what are the characteristics, like the wavelength, the period, direction of travel, location, altitude of traveling ionospheric disturbances, these Doppler shift measurements of WWV that people like David Kazan and the CASE students are doing, along with people like Steve Serwin. That could help answer those questions. What is the location and nature of the sources that drive the traveling ionospheric disturbances? So is it upper atmospheric winds and tides and upper atmospheric forcing? And you can learn more about this during Larissa's tutorial tomorrow. I'm sure she'll probably talk about some of these things, right? Yes? Okay. Just double checking. What is the location and nature of ionospheric variability that is not associated with PIDs? And how does the location nature of ionospheric variability sources change from quiet to disturbed times? Functional requirements, we want to make measurements on a minimum of 2, but really multiple transmit-receive paths with lengths greater than about 100 kilometers and good spatial distribution for good orthogonality properties, because these disturbances that we're looking at typically have wavelengths of around 100 or more kilometers. All right, and then the final objective I have is to determine the impact of space weather events and ionospheric variability on terrestrial HF communication systems. And this is the objective that's less scientific, but really speaks to, the ham radio community, like the contest community, right? They want contesters and emergency communicators. They really want to know, how does this space weather affect our communication? So the questions could be, what propagation paths are open and closed for given space weather conditions? What is the dominant propagation mode, i.e. single hop, double hop, ducting for given space weather conditions? We saw that in Steve Serwin's presentation this morning, single versus double hop. What are ionospheric variability effects on HF communication signal parameters, such as amplitude and phase scintillation, channel fading, and polarization? And functional requirements, we want to receive swept frequency sounder signals from appropriately polarized or non-polarized signals of opportunity. Again, maybe CODAR, or now also Digisond or chirp sounders, or we can talk about other possible sources. So that's all I have for now. I think, am I out of time? I have time for questions. So we have time for a couple questions and a little discussion. But remember, continue this discussion throughout the breaks and during the panels tomorrow and during the demo room. So keep thinking about this. And I can put these slides on the HamSci website right away. I can put it on the program page, and that way you can start talking about them now. Okay? Yeah.
Just a slight point of clarification. So if you go back to the second objective, we had 100 kilometers in there. That's also from a geometric point of view, is that if you have a source, if you're trying to look at the E and F region ionosphere, if you move the stations too far apart, the elevation angles get low enough that you're confusing. You have a long path through the ionosphere, and typically if you're looking at the E region and the F region, stations that are separated at 100 or a couple hundred kilometers, if you think about a triangle, are about right. We could see fluctuations that are, of course, at shorter wavelengths or longer wavelengths than that, but if your sampling includes a lot of baselines on that level, you're going to have less ambiguity about what you're measuring, because you are, with a lot of these things, you're measuring a path length. You're not necessarily measuring an altitude resolved thing. So.
All right, thank you. So I'll put a PDF of these slides on the Space Weather station page, and also right on the top of the agenda page too, so it's easy to find. Okay?